Breaking the norm. Diagonalizable rebels. Today, we'll explore a mathematical paradox where a non-normal matrix still manages to be fully diagonalizable. In our problem today, A22, we're told to consider the matrix M that is symmetric 2 by 2, composed of the elements 1, 1, 1i. For part A, we're asked, is it normal? And B, is it diagonalizable? Now, if this thing is true, we know that the diagonalizability is also true. But is the contrapositive true? Let's find out. So, the test for normality is really a test about the commutativity of the matrices. As such, what we need is M and M dagger. Since the dagger is the conjugate transpose or the adjoint, we know that being a symmetric matrix doesn't really change this, but the conjugate puts that as a negative I. As such, the normality condition A.82 states that we need the commutator of M dagger M to equal 0. So if we expand this commutator, that is M dagger M minus MM dagger, and that still has to equal 0. So if we add this thing over to this side, we see we get the statement of commutativity. So this is really what this test is about with the dagger. Okay, because we've seen how the matrix being Hermitian or unitary, very special properties. We like them with their eigenvalues, their diagonalizability, this, that, and the third. Very, very useful things to have. So asking, is it normal, makes a lot of sense. And it's a quick calculation. That being said, all we need to do is find the matrix multiplication for this side and see if it's equal to this side. So let's see what we get. So M dagger M, we see that we have our two matrices. This row to this column gives us our first element. First row to second column gives us this element. Second row to first column gives us this. Second row, second column to this. So now once we simplify that, we just see we get 1 plus 1, 1 plus I, 1 minus I, and 1 minus I squared. So the I squared we have to take care of. We know that I squared is equal to negative 1, so the two negatives cancel. 1 and 1 give us 2. Pretty easy computation, all things considered. So outside of these two non-diagonal elements, everything's pretty good, but clearly the non-diagonal elements being conjugates of one another should tell us something. So to recap, this is what we found for the left-hand side. Now let's compute the right-hand side. All we do is switch the positions, row, column, row, column, row, column, row, column. We see what we get here. Notice that it kind of looks like the transpose of our last one. So if we go ahead and compute this all the way through, we get the negative I down there again. And then we just see that the negative I turns to negative 1. So we cancel, and then we get 2, 2, 1 minus I, 1 plus I. And as you see, these look like conjugates of one another or transposes of one another, but not transpose conjugates. Very weird, but very insightful. And that should give you a key to what's coming next. So that was one of two things to note. The transpose should be insightful for later, and that's what we like. But since they do not equal, we're not normal. And in fact, the commutator, which is supposed to be 0, is if we take the difference of these two things, we see that our main diagonal terms here cancel. 0, that cancels to 0, cancels to 0. 1 and 1 cancel, 1 and 1 cancel. So we're left with this matrix of plus 2i here, minus 2i there. Just not going to work. It's not 0, so the commutator not being 0, we're non-normal. But the question we have to ask now is, just because it's non-normal, does that mean it's non-diagonalizable? So now we get to the diagonalization phase of this. And so a couple words regarding diagonalization. It is well established that all the normal matrices are diagonalizable. However, the contrapositive of this statement does not necessarily hold true. Okay, so just because I'm not normal doesn't mean I'm necessarily not diagonal. So that's what we have to show here. So in order to find the diagonalizability, we have to find the eigenvalues and see if they're distinct. So to find the eigenvalues, we employ equations A.22 and solve the characteristic polynomial. And as such, we need to find the difference of this for the determinant of m minus lambda I, where we see m multiply lambda into the identity matrix. Go ahead and distribute that. Thank you, vector space axioms. And then take the element y's difference. Now that we have that, we're good to go for the determinant. And the determinant, again, needs to equal 0. We need to be singular. Thankfully, it's a 2 by 2 determinant, so we know that we can just do a crisscross and we'll be fine. So element A, element D, minus BC, again, equals 0. Let's go ahead and distribute the curly brackets. So then we see we end up with a kind of a polynomial going on here. Not kind of, but a polynomial. This will be simplified to the characteristic polynomial, which is what we see here. Note that this is an ugly polynomial with these complex coefficients. So let's employ the quadratic equation. Well, plugging everything into our quadratic equation, kind of gross, very messy. And for the patrons, I did include in the PDF the actual eigenvalues of these. And trust me, they're not nice, or the eigenvectors of these, and they're not pretty. As you can see, we're going to have to find this simplification. Let's start. We see that the negative signs here and here cancel. We can factor out the -1 here, as we see there, because then squaring it will lead that to a positive number, and then we could square this and distribute it, as well as dump this 4 into the curly brackets. So dumping the 4, we see that there. We'll have to dump that negative in soon. This 1 squared goes to, or -1 squared goes to 1, and then we just FOIL out this thing here, the 1 plus I squared, leaving us with this. With the negatives canceled, that cleans up our leading term. Now we see that once we distribute that negative into this curly bracket, simplify this I squared into a -1, we see we get 1 and 1 canceling, and then we see we have a plus 2i and now a minus 4i. That simplifies to minus 2i, and this is our eigenvalue set of eigenvalues. Notice that this plus or minus sign is here. And the presence of this plus or minus sign shows you that we have 2 distinct eigenvalues. And this necessitates the existence of 2 linearly independent eigenvectors. As such, they collectively span the eigenspace or the vector space in question. So consequently, this matrix exhibits diagonalizability. And this is despite its non-normal nature. So again, what this says is that being normal is a sufficient condition for diagonalizability, but not a required one. Very, very insightful. Short video, but a fun one. Again, the normal matrices will come up again, so be prepared for that. If this video got you thinking, imagine what's coming next. Subscribe and join our community for weekly insights into the world of physics. There's so much more to uncover, and I'd love to have you along for the journey. I just want to take a moment to thank my incredible Patreon supporters. Your support is truly the backbone of this channel. It's because of you that I can keep creating these videos and diving deep into the fascinating world of physics with everyone. Your contributions make a real difference in helping me bring these concepts to life, and I'm so grateful to each of you for believing in this journey. And if anyone else is interested in supporting this channel and joining our Patreon community, you can check out the link in the description below. Together we can keep exploring the wonders of science and discovering even more amazing things. As always, thank you for watching. Until next time, stay curious.